Today we're going to talk about atmospheric circulation, or how wind moves around the globe. Now remember, we looked at this graph before. We talked about how solar radiation is more focused at the equator because the same amount of radiation is focused on a smaller area. The consequence of that is that there's an imbalance of incoming solar radiation or incoming energy around the globe. Now this graph shows the equator at the middle and the north and south poles at either side, and the red line is the amount of incoming solar radiation in 1 year. That heat that is focused in the latitudes that are near the equator needs to be moved towards the poles, and so that heat transfer is accomplished by both ocean and atmospheric currents. Now this is a map similar to the one we looked at before of ocean temperatures. This one is the net solar radiation, how much solar energy is absorbed, incoming solar energy is absorbed by the land and the oceans across the globe. And it would be, again, quite even in terms of its color stripes if the globe was homogeneous, but it's not. We see continents, we see ocean basins of various depths, and so there are differences across the globe. If you focus just on the equator from the Atlantic across South America and into the Pacific, you can see some of the effects that continents have. The incoming solar radiation is equal in all of those places, but more of it is absorbed in the Pacific Ocean, which is a much bigger, deeper ocean basin than the Atlantic, and certainly more of it is absorbed in the oceans than on the land. Even in the Pacific Ocean, just to the west of South America, because that ocean basin is shallower, less incoming radiation is absorbed in that part of the Pacific than further to the east. That's just one of the things that you can see on this map. Others you'll look at later. Now you know convection. Convection's pretty straightforward. We've looked at it in the mantle. Warm air rises, cool air sinks, and so the very simplest explanation of air convection you can make for the Earth is that because there's more heat at the equator, warm air will rise at the equator and it will fall at the poles. And therefore, air will be transferred in the upper atmosphere towards the north or towards the south, and it will be transferred along the surface of the Earth from the poles to the equator. So that would work beautifully if the Earth was all homogeneous and not moving. But of course, the Earth is spinning, and the Coriolis effect will affect the air currents as well as the ocean currents. What it does for the air currents is it breaks them up. And the result of that is that instead of a simple convection cell in the atmosphere, we see 3 in the northern hemisphere, 3 in the southern hemisphere. So let's start at the equator again, at this very first circulation cell called the Hadley Cell. And just as we expect, warm air is rising at the equator. It's moving in the upper atmosphere towards the north and towards the south, but it's falling at 30 degrees north or south, not all the way at the pole. And it's moving along the surface back towards the equator from 30 down to 0. And then the next band runs from 30 to 60 degrees, and if air is sinking, air coming from the south is sinking at 30 degrees, then air coming from the north better be also moving in the same direction, down at 30 degrees north or south latitude, and then away from that mark. So air currents are traveling towards the north, towards 60 degrees, or towards the south, towards the 60-degree line. And there again, relatively warm air is rising, and it is sinking at the poles. So 3 circulation cells that are 30 degrees wide each on the surface of the Earth. This has really profound implications for climate across the globe, and let me just give you 2 quick examples. Of course, you know at the equator that tropical climate tends to be warm and wet, and that's because warm air is rising. It brings with it, warm air can hold a lot of moisture, so it brings a lot of evaporation with it, and it creates rain, and that's why they've drawn clouds here for you along the equator. That's what tropical weather is. Did you know that at 30 degrees north latitude and south latitude, you'll find a lot of deserts? That's where deserts are concentrated, because cool air coming from the upper atmosphere down to the earth is dry air. So let's look at a simpler drawing of this, take away some of the three-dimensionality of the last one, and just look at the combination of wind currents along the surface and what they look like globally. So let's look at these red lines here that are labeled the trade winds. The air currents between 0 and 30 degrees north latitude, because of the Coriolis effect and because of the air circulation, are moving from the east towards the west. And we call them easterly winds because we always name winds from the direction they're coming from. And so the trade winds are easterly winds. They blow from the east to the west between 0 and 30 degrees. And notice they don't cross the equator. Then between 30 and 60 degrees, we have the opposite wind pattern blowing. We have winds that are coming because of the Coriolis effect from the west to the east, so we call those the westerly winds. And then the polar winds are also moving towards the east. So these three bands of winds, the trade winds, the westerlies, and the polar winds, blowing in opposite directions, and the breaking point, the changing point, is at about 0 and 30 and 60 degrees, following the air circulation patterns. So this is a map of the US, and the westerly winds are really dominant here. The 30-degree line is right through Texas, actually. So we are kind of on that line between where the westerlies blow and where we get into tropical winds. So you can see the westerlies all across the western US in this wind map, and they come all the way across the northern part of Texas and hit Dallas, and then they run into something coming off the Gulf, and that is not a northerly wind. That's not a westerly wind or an easterly wind. It's a wind that's blowing from the south towards the north. So the other thing that is really strongly influencing wind patterns locally is the relationship between continents and oceans. Now, we very commonly get this wind pattern in Texas where the winds are coming off the Gulf. In this case, happened to be a pretty tough day. The winds coming off the Gulf are blowing all the way up into Canada. Why do they do that? Well, they do that because land and sea absorb heat differently. Water is a very good thermal absorber and land is not. And so when the same amount of sun hits the Gulf of Mexico and the land around it, the Gulf just absorbs the heat and warms up. The land absorbs it for a little while, but then starts reflecting it back. So warm air is rising off of the land, and air has to rush in to fill it. And where does it come from? It comes from the Gulf. And so this happens to probably be a pretty warm day across the Midwest, a lot of air rushing in off the Gulf to fill the space where the warm air is rising off the continent. Wind patterns affect a lot of things. One thing they affect is the track of hurricanes. And I want to make a couple of points looking at this map. One is that the hurricanes do not cross the equator and they don't land in the equator. They are in the band north of the equator or south of the equator, but directly at the equator, the wind just isn't strong enough to move hurricanes. It's a pretty calm place right at the equator. The other thing I want you to note is that, well, we're very focused on hurricanes that hit the U.S., the Atlantic hurricanes and Gulf hurricanes. There are much more and stronger hurricanes in the eastern Pacific than there are in the Atlantic, and that is partially due to the much larger ocean basin that the Pacific is. So that's it. That's atmospheric circulation in